All right, welcome to section 3.4, zeros of polynomial functions. When finding zeros of polynomial functions, what kinds of numbers can we get? Here's a quick example that involves all possible kinds of zeros. So we have f of x. F of x is written in linear factorization form. Each of these linear factors, when set equal to 0, will give us the zeros of f of x. So we have our zeros here in this row. We have -3 and 1/2, which represent rational zeros. We have -√2 and √2 that represent irrational zeros. And we have 4 minus 5i and 4 plus 5i that represent complex imaginary zeros. Now, rational zeros and irrational zeros represent the real zeros of f of x, whereas our complex imaginary zeros represent non-real zeros. And that's because they contain the symbol I. Recall that a polynomial function of degree n can have at most n real zeros. Real zeros can be rational or irrational. Rational zeros are those that can be written in the form of a fraction p divided by x. Objective 1. Use the rational zero theorem to find possible rational zeros. The rational zero theorem can be used to determine all possible rational zeros of a polynomial function. Not all possible zeros will be a zero of the function, but every rational zero of the polynomial function will appear somewhere in the list of possible zeros. The rational zero theorem says, if f of x has integer coefficients and a subscript n does not equal 0, and if p divided by q, written in lowest terms, is a rational zero of f, then p is a factor of the constant a sub 0, and q is a factor of the leading coefficient a sub n. In other words, if a rational zero exists for a polynomial, then it must be of the form p divided by q, where the factors of our constant term are divided by the factors of our leading coefficient. And so this is going to be how we will solve for all possible rational zeros of a function. So in our first example here, we're asked to list all possible rational zeros for each function. So for a, we have f of x equals 3x cubed minus x squared minus 18x plus 16. Okay. So we will take p divided by q, where p represents the factors of 16, our constant term, and q represents the factors of 3. And 3 is our leading coefficient. Now the factors of 16 are plus 1, plus 2, plus 4, plus 8, and plus 16, plus or minus. And the factors of 3 are plus or minus 1 and plus or minus 3. Okay. So our possible zero will be all of the combinations that we get when we pair a value in the numerator with a value in the denominator. In other words, I'm going to take all of the values in the numerator and I'm going to divide it by the first value in the denominator, which is 1. So 1 divided by 1, 2 divided by 1, 4 divided by 1, 8 divided by 1, and 16 divided by 1. And that's going to get me the values plus or minus 1, 2, 4, 8, and 16. I'm going to take all the values in the numerator and divide it by 3. So that'll give me plus or minus 1/3, 2/3, 4/3, 8/3, and 16/3. Okay? And so these are all of the possible zeros of f of x. B, f of x equals 6x to the fifth minus 8x cubed plus 9x squared minus 12. Okay. So we'll take p divided by q, where p is going to be the factors of 12, and q is going to be the factors of 6. So the factors of 12 are 1, 2, 3, 4, 6, and 12. And the factors of 6 will be 1, 2, 3, and 6. So now let's list out all of the possible zeros. So we know all of the values in the numerator divided by 1 are the values in the numerator. Okay. Now we'll divide all the values in the numerator by 2. So we will have 1/2. We will have 2 divided by 2, which is 1. 1 is already in our list, so we don't have to write it again. Then we have 3 over 2. 4 divided by 2 is 2. 6 divided by 2 is 3. And 12 divided by 2 is 6, which are already present in our list. Now we'll take all the numbers in the numerator and divide it by 3. So we'll have 1/3. We will have 2/3. 3 divided by 3 is 1. Then we'll have 4/3. 6 divided by 3 is 2. And 12 divided by 3 is 4. And then our last one is 6. So we'll have plus or minus 1/6. 2/3. 2/6 is 1/3, which is already present. And then we have 4/6, which is 2/3, which is already present. And then 12 divided by 6 is 2, which we already have as well. So these are all of the possible zeros of f of x. Okay. All right, this is a checkpoint. So let's see if you understand the concept. List all the possible rational zeros of f of x. So pause the video, and once you finish, return to check your answer. All right, so here is the solution to our checkpoint. So you should have gotten the possible zeros: 1, 2, 3, 4, 6, 8, 12, 24, 1/2, and 3/2. Objective 2, find zeros of polynomial functions. So we are going to now find the actual zeros of our polynomial function. The first step we're going to take is we're going to list all the possible rational zeros using the rational zero theorem. Then in step 2, we'll test the zeros using synthetic substitution or division. Step 3, when you find a zero that works, we'll use the remainder to completely factor the polynomial and then find the zeros. Remember, if the degree of a polynomial function or equation is 4 or higher, it is often necessary to find more than one linear factor by synthetic division. One way to speed up the process of finding the first zero is to graph the function. Any x-intercept is a zero. So for our first set of problems here, we're asked to list all possible rational zeros and then find the actual zeros. So for our function f of x here, let's list the possible zeros. We do that by first starting out with p divided by q, where p is our constant and q is our leading coefficient. So the factors of p are 1, 2, 5, and 10. the factors of Q are 1 and 3. So this gives us the possible zeros 1, 2, 5, and 10. Then we'll have 1/3, 2/3, 5/3, and 10/3. Okay. Now that we have the possible zeros, we are going to test to see which possible zero is an actual zero. Okay, so let's start off with -2. Right, so I'm going to set up my synthetic division. I'm going to take the coefficients of my terms in f of x. So that's 3, -8, -33, -10. And then I'm going to do synthetic division, bring down 3, multiply, then I'll add, multiply by -2, then I'll add, multiply, and then I'll add, and I get a 0 as my remainder. So I know that -2 is an actual 0. So f of x equals x plus 2, that is the linear factor of the 0, -2. And then my depressed polynomial, which is 3x squared minus 14x minus 5. When I write 3x squared minus 14x minus 5 in factored form, I now have f of x in complete factored form. Now that it's in factored form, linear factored form, I can now find my zeros, and I do that by setting each of these linear factors equal to 0. Okay? So x plus 2 equals 0, 3x plus 1 equals 0, and x minus 5 equals 0. So x equals -2, x equals -1/3, and x equals 5. So my actual zeros are going to be the values -2, -1/3, and 5. Now, what if I tried a 0 and I didn't get a 0 as my remainder? So say I tried -1 and my remainder was a value other than 0. Then I know that -1 would not be a 0 of this function f of x. So you want to keep testing zeros until you get a remainder of 0. Now, of course, a quicker way to do this is to graph f of x in your calculator in the y equals. Go to the table and find a 0 by locating an x-coordinate whose y-coordinate is 0. That way you can just get this process started of synthetic division and then continue with factoring. B. F of x equals x to the fourth plus x cubed minus 31x squared minus 61x minus 30. So let's first find the possible zeros. So this is going to be p and then q, which would be 1. So p will be the factors of 30, which is 1, 2, 3, 5, 6, 10, 15, and 30, divided by q, which would just be 1. So my possible zeros are going to be all of the values in the numerator. So 1, 2, 3, 5, 6, 10, 15, and 30. So to get started, I would take my function f of x and plug it into my calculator in y equals. I would go second graph to go to my table, and I would then see that I have a 0 at -1. So let's divide our polynomial by -1. So we'll set up our synthetic division. Now my calculator told me that -1 is a 0, so that means I should get 0 in my denominator, or in my, not my denominator, in my remainder. So the last digits should be a 0. So let's start the process, bring down the 1, multiply, add, multiply, add, multiply, add, multiply, and add. And I got 0, which is great. Okay. Now, if I were continuing to look at my calculator, I would also see that -5 is also a 0. So I can actually continue dividing my depressed polynomial by that 0. So I'm going to bring down 1, and I will multiply, add, multiply, add, multiply, add, and I got 0 again, which is great. Now, you might have also seen that 6 was a 0, and so you could continue this process to 6. We're just verifying all of the zeros while also getting our polynomial f of x in factor form. So let's bring down the 1, multiply, add, multiply, add, and I got 0. So let's now write f of x in factor form. So we started off by dividing our function f of x by -1, which is a linear factor of x plus 1, which gave us x cubed minus 31x minus 30. Then we factored that, or I guess we divided x cubed minus 31x minus 30 by -5, which has a linear factor of x plus 5, and we got x squared minus 5x minus 6, and then we divided that quadratic by 6, which gave us the linear factor x minus 6 and a depressed polynomial of x minus 1. Okay, so we have actually x plus 1, sorry, x plus 1. So we have the factored form of f of x, which is x plus 1 squared times x plus 5 times x minus 6. So setting each of these linear factors to 0, we get x equals -1, x equals -5, and x equals 6. So the actual zeros of f of x are -1, -5, and 6. Okay. Now the linear factor x plus 1 has a power or an exponent of 2. So that means that -1 has a multiplicity of 2. So if we were to graph f of x, we would have to take note of that. All right. So here's your checkpoint. So I want you to list all the possible rational zeros and then find the actual zero. So just what we did together. All right. So we're going to pause the video. I want you to attempt A and then come back and check. Right here is the answers to A. So the zeros you should have gotten are -4, -1, and 2. Now pause and attempt B. The answer you should have gotten for B, the actual zeros are -3, -2, -1, and 3. And our last checkpoint, C, pause and attempt C. Right here is your solution for C. The actual zeros are -1, 3/2, and 2. Objective 3, solve polynomial equations. So just as polynomial functions can have real zeros, rational or irrational, it can also have complex zeros. The properties of roots of polynomial equations are 1. If a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. And 2, if a plus bi is a root of a polynomial equation with real coefficients where b doesn't equal 0, then the imaginary number a minus bi is also a root. Remember, imaginary roots, if they exist, occur in conjugate pairs. So if I have a 0 that's 7i, its conjugate pair would be -7i. If I have a 0 that is 2 plus 6i, then its conjugate pair, 2 minus 6i, would also be a 0. So in these examples, we're asked to find all zeros of the polynomial function below, and then simplify all irrational and complex solutions. So here we have f of x equals 3x cubed minus 30x squared plus 71x plus 6. And we want to find all of its zeros. So the first thing we need to do is state the possible zeros. And to do that, we're going to take p divided by q, where p are the factors of 6 and q are the factors of 3. So p would be 1, 2, 3, and 6. And q would be 1 and 3. So the possible zeros are going to be 1, 2, 3, 6, 1/3, and 2/3. Okay, because 6 divided by 3 is 2, and that's already in our list. So we will enter this into our calculator, and we will try and find a actual zero by using the second table. And you would see that 6 is one of those actual zeros. So let's set up our synthetic division to get our function in vector form. So 3, 30, 71, and 6. Bring down the 3, multiply, add, multiply, add, multiply, and add. Let me see here that 6 actually is a zero of f of x. Okay? So this will give us the factored form of x minus 6 times 3x squared minus 12x minus 1. So now we want to try and factor this quadratic. Right? And in attempting to factor it, we would find that the normal means of factoring a quadratic aren't applicable to this equation. So we would have to use a different process to write this in factored form or to find the zeros that would make this quadratic equal to 0. So we'll set x minus 6 equal to 0, and we know that that 0 is 6. And when we set 3x squared minus 12x minus 1 equals to 0, we can't write it in factored form, so we're going to use the quadratic formula to help us find the x values that make our equation statement true. Okay? So this is our quadratic formula. So substituting in, we have negative 12 as b, the square root, negative 12 squared minus 4a times c, all over 2 times a. And this will get us 12 plus or minus the square root of 156 over 6. Simplifying, we get 12 plus or minus 2 square root 39 over 6. I can divide each of the numbers or terms by 6, not by 6, by 2. And I would get 6 plus or minus the square root of 39 over 6. So just for review with square roots, if I have the square root of 156 and I'm trying to simplify it, I want to find a perfect square that is a factor of 156, and that is 4. So 4 times 39 equals 156. Using the properties, I can split the square root into 2 factors, which will allow me to simplify the square root of 4, giving me 2 square root 39. Okay? So my final answer, the actual zeros of f of x, would be 6 and 6 plus or minus the square root of 39 over, I divided everything by 2, so this should actually be 3. There's an error. Should actually be 3. So if I divide this by 2, I get 6. Divide this by 2, I get 1. Divide this by 2, I get 3. Okay. So we have 6, which is a rational 0, and then we have 6 plus or minus square root 39 over 3, which is a complex 0. It's not an imaginary because there's no imaginary numbers. It's just complex because we have a square root 39, which is not simplifiable. Let's do B. So this is going to be our P. This will be our Q. So P divided by Q. So the factors of 5 will be plus or minus 1 and 5. And the factors of 2 will be plus or minus 1 and 2. So our possible zeros will be plus or minus 1, plus or minus 2, not 2, plus or minus 5, plus or minus 1/2, and plus or minus 5, 2. So I would utilize my calculator to find a 0 to start off with, and I would see that 1 is a 0. Okay. Now I'm going to set up my synthetic division. I'm taking note that the powers 3 and 2 are not present, so I'm going to have to put zeros as placeholders for those powers, and then start my synthetic process. So I'll multiply, add, multiply, add, multiply, add, multiply, add, multiply, and add. Excellent. Okay. In my calculator, I would have also noticed that -1 is also a 0, so I can continue the process. So 2, bringing it down, and then multiplying, add, multiply, add, multiply, add, multiply, and then add. Okay. All right. So when I divided f of x by 1, my factors were x minus 1, x minus 1, x minus 1 times 2x to the 4 minus 3x cubed minus 3x squared minus 3x minus 5. And then I divided by -1, that's factors x plus 1, and I got 2x cubed minus 5x squared plus 2x minus 5. Now I need to continue the factorization, but 2x cubed minus 5x squared plus 2x minus 5 needs to be factored as well. So when I perform factor by grouping, I will get x squared plus 1 times 2x minus 5. Now f of x is completely factored, so I can set each of my factors equal to 0 to find the zeros of my polynomial function. When I do, I get x equals 1, x equals -1. This would be x squared equals -1, so then x would equal plus or minus I, and then we'd have x equals 5/2. So the zeros of f of x are 1, -1, plus or minus I, and 5/2. Excellent. All right, let's do one more. So here for C, we have f of x equals x cubed minus 2x plus 6x plus 48. Okay. So we're going to take p divided by q in order to find our possible zeros. 48 is p, 1 is q. So in other words, we are going to take the factors of 48, which are 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48, and divide that by the factors of q, which is just 1. So our possible zeros are 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. Okay. Plugging our function f of x into our calculator, we see that we have a 0 at -2. So we're going to set up our synthetic division, 1, -2, 16, and 48. Bring down the 1 and start the process. Multiply, add, multiply, add, multiply, and add. Excellent. Okay. So we have f of x equals x plus 2 times x squared minus 4x plus 24. Now we need to write this quadratic in factored form so that f of x is completely factored. There isn't any value that multiplies to get 24 and adds to get -4. So we then need to use the quadratic formula. So when we set our factors equal to 0, they will then give us the zeros for f of x. So to find x, we're going to use the quadratic formula. To find our zeros. So we have -4 plus or minus -4 squared minus 4 times 1 times 24 all over 2 times 1. So x equals 4 plus or minus the square root of -80 over 2. This simplifies to 4 plus or minus 4i square root 5 over 2. Dividing by 2, we will get x equals 2 plus or minus 2i square root 5. So to show that middle process of simplifying the square root of -80, I know that -80 is -1 times 80. The square root of -1 is I. Okay, so now I just need to simplify 80. Now 80 contains, I should say, the perfect square 16. So when I break up this square root, I'll be able to simplify the square root of 16, giving me 4i square root 5. So my actual zeros of f of x are -2 and 2 plus or minus 2i square root 5. Awesome. Yay. Objective 4. Use linear factorization theorem to find polynomials. So the fundamental theorem of algebra says that if f of x is a polynomial function of degree n, where n is greater than or equal to 1, then the equation of f of x equals 0 has at least one zero in the complex number system. So do all polynomial functions or equations have at least one imaginary root? No, they all don't. But as you read in the fundamental theorem of algebra, don't confuse complex root with imaginary root and conclude that every polynomial equation has at least one imaginary root. Recall that complex numbers include both real numbers and imaginary numbers. Linear factorization theorem says if c is a complex zero of a polynomial function, then x minus c is a linear factor of the polynomial. Remember, we can use the linear factorization theorem to find a polynomial function when the zeros are given. So we're going to be working backwards. So for our examples, we need to find an nth degree polynomial function with real coefficients satisfying given conditions. If you're using a graphing utility, you can use it to graph the function and verify the real zeros and the given function value. So given that 1 minus 5i is a zero of f of x, we're asked to find the remaining zeros and factor f of x as a product of linear factors. So since 1 minus I is a zero of f of x, we know its conjugate 1 plus 5i is also a zero of f of x. So let's divide f of x by our zeros so that we can get it in factored form. All right, so we have 1, negative 3, 28, and negative 26. So we bring down 1. We can multiply. So 1 minus 5a. We can only combine like terms, so that would be negative 3 and 1. So that would be negative 2 minus 5i. Then we'll need to multiply these two terms together. So let's do that in here. So we have 1 minus 5i times negative 2 minus 5i. We'll do FOIL, so we'll get negative 2 minus 5i plus 10i plus 25i squared, which gives me negative 2 plus 5i plus 25i squared. I squared equals negative 1. So I have negative 2 plus 5i minus 25. So that's negative 27 plus 5i. So I have negative 27 plus 5i. I'm going to add 28. So I'll have 1 plus 5i. So now let's multiply those two together. So 1 minus 5i times 1 plus 5i. So I'll have 1 plus 5i minus 5i minus 25i squared. These terms cancel. So I have 1 minus 25i squared. 1 minus 25 times negative 1 makes 1 plus 25, which equals 26. And then 26 minus 26 is 0. Excellent. So now let's do the conjugate, 1 plus 5i. So we bring down the 1, multiply. So the imaginary roots cancel. And then that leaves me with negative 1. When I multiply negative 1 times 1 plus 5i, I have to distribute the 1. Right? The imaginary roots cancel again, and so do the reals. So that leaves me with 0. Excellent. So f of x as a product of linear factors would be x minus 1 minus 5i, x minus 1 plus 5i, and x minus 1, which is the corresponding. So why don't we simplify this? I'll put x minus 1 plus 5i, x minus 1 minus 5i, and x minus 1. So my actual zeros are 1, and 1 plus or minus I. So that was kind of fun. All right. Given that x equals -1/2 is one solution to this equation, 2x to the fourth minus x cubed plus 17x squared minus 9x minus 9 equals 0, find the remaining solutions. All right, we're going to give this function a name, and it's going to be f of x. So to find the possible zeros of f of x, where p is 9 and q is 2, the factors of p are 1, 3, and 9. The factors of q are 1 and 2. So its possible zeros are 1, 3, 9, 1/2, 3/2, and 9/2. Now we know that -1/2 is a 0, so we can start with that 0. Okay? So we're going to put all of our coefficients, so 2, -1, 17, -9, and -9. We'll bring down 2, multiply it by -1/2. We get -1, we'll add, we'll multiply again, and we'll add, then we'll multiply again, then we'll add, and multiply, and we get 0. Okay? Now, we know that -1/2 is a 0, but if we wanted to find any other zeros, we could. Okay? And we can do that by putting f of x into our calculator. And we would also find that 1 is a 0. Now, if you didn't find any other 0, that would mean that you either have a complex 0 or an imaginary root. Okay? So let's bring down the 2, multiply, add, multiply, add, multiply, and add. Awesome. So we have f of x equals 2x plus 1. That's the linear factor for -1/2. And then that gave us 2x cubed minus 2x squared plus 18x minus 18. And then when we divide it by 1, we got 2x squared plus 18. Okay? Now, when we set both of these to factor form, when we set all of our linear factors to 0, we can then find the zeros, actual zeros of our equation. So we know this one equals 1/2. We know this one equals 1. Over here, we're going to have to subtract 18 and divide by 2. And so x will equal plus or minus 3i. So we have imaginary zeros. So the zeros of our equation, or remaining solutions of our equation, are 1 and plus or minus 3i. Okay, awesome. C. We are asked to find a polynomial f of x of lowest degree with zeros of 3i and 2, multiplicity 2. So we know the degree of our polynomial is going to be the lowest possible. Okay? And we have zeros given to us in our problem. We have 3i, which has multiplicity 1. Let's say of 1. There we go. And we have 2 that has a multiplicity of 2. Since 3i is a 0, we know its conjugate, negative 3i, is also going to be a 0. And that's going to have multiplicity of 1. So to find this polynomial, we're going to take f of x equals a times the product of its linear factors. So that would be x minus 3i, x plus 3i, and x minus 2, but that would have an exponent of 2 because it has a multiplicity of 2. So then we would need to multiply these through. So this would give us x squared plus 9. And this would give us x squared minus 4x minus 4 when we FOILed all the way through. Then we would have to distribute one more time, which would get us x to the 4th minus 4x cubed plus 13x squared minus 36x plus 36. All right, and so that would be our polynomial of lowest degree. A represents what the leading coefficient could be by. Multiply that. Let's do another one. So here we have a polynomial p of x of degree 3. So we know that its highest power is going to be 3. And it has zeros negative 2i and 4. And the polynomial must also satisfy the condition p of 0 equals 32. Okay. So our degree is 3. We have zeros negative 2i with multiplicity of 1 and 4 with multiplicity of 1. Since negative 2i is a 0, positive 2i would also be a 0, and that would have a multiplicity of 1 as well. Okay? So let's find the standard form of px. So that will be a times the product of its linear factors, x minus 2i, x plus 2i, and x minus 4. So multiplying the linear factors with I, we'll get x squared plus 4, which we would then need to FOIL with x minus 4, which would get us x cubed minus 4x squared plus 4x minus 16. Okay. But now we need to apply our condition. And our condition says that p of 0 equals 32. That means 32 equals p of x where x is 0. So I'm going to substitute in 0 everywhere there is an x. Okay. Now I can simplify that down because anything times 0 is 0. So that leaves me with 32 equals negative 16a. When I divide both sides by negative 16, I get negative 2. Okay. So p of x equals negative 2 times x cubed minus 4x squared plus 4x minus 16. When I distribute the 2 to every term, the negative 2, I'll get negative 2x cubed plus 8x squared minus 8x plus 32. And that is the polynomial for p of x. All right. Here is your checkpoint. You want to find the third degree polynomial function f of x with real coefficients that has a -3 and I as zeros, such that f of 1 equals 8. Okay? So why don't you pause and attempt this checkpoint. All right, here is the solution for your checkpoint. You should have gotten f of x equals x cubed plus 3x squared plus x plus 3. All right, and that concludes the section for 3.4.